Okay, so today I'm going to talk about investigating portable heterogeneous solutions using FastCalometer simulation for Atlas. So a little bit of history. Why did we choose FastCaloSim? Well, Atlas obviously needs a lot of simulation, like many other experiments, for standard model and background modeling, detector and upgrade studies. And as we know, the demands for this will only get worse for Run 3 and beyond. A large fraction of Atlas's computational budget is spent simulating the liquid argon calorimeter. And there's a fast parameterized simulation package which has been developed for this, which speeds things up enormously over the G4 full sim. There's also been a CUDA port of FCS which was developed, which is small, self-contained, and has very few external dependencies. So it's like a perfect test bed for our portability studies. So the liquid argon calorimeter actually has a lot of inherent parallelism, and so we did some profiling studies to see what could be effectively offloaded. And there is, if we ignore the not inconsiderable amount of time spent reading in data and parameterization files, we see that there is this big chunk of time which can actually be parallelized very nicely over a large number of hits. And the number of hits can actually vary between a few hundreds to 25,000. And so this looks like a very good candidate for running onto a GPU. So we took this code, we modified the data structures to make them compatible with GPUs, re-implemented the geometry, and we wrote the code to have basically 3 different types of kernels. One which does some memory reinitialization, there's a main simulation chunk, and then there's a reduction step which does a bunch of counting and some memory coalescing before moving things back to the CPU. If we actually look at the performance of the CUDA port, and here I'm just going to start talking about the event loop time, so ignoring all the I/O that gets done at the beginning of the event. In this plot, we see the performance of the GPU code over the CPU code, and we do it in 2 different ways. We can either look at the performance of the GPU on a single event, or if we can also group the data between multiple events to give more work to the GPU. And what we can see is with a number of different detector regions and different types of particles that are being used in the simulation, we see significant improvements over the CPU code, except in things like very far forward regions of the detector where there really isn't a lot of work. And obviously we see much better performance when we group the work between multiple events because the GPU has much more work to crunch on. And this actually shows a significant flaw with the FastCalometer simulation code, which is that the kernels tend to be very, very short because there really isn't a lot of work to be done. And so we tend to be limited by the launch latency. If we increase the particle energies, which really offers a lot more work on the GPU, we see much better performance, up to in some cases 50 to 60 times improvement over the CPU. So then we took the CUDA code and we ported it to Kokkos. Now, Kokkos requires you to select a single device parallel backend and a single host parallel backend for any compiled Kokkos library. Now, in theory, you can run both device and host parallel backends in the same code, but this really complicates things because you can't use a default execution space. So you really have to say where each kernel has to go. You also can't expose plain the Kokkos headers rather to plain NVCC. So you have to do some selection macros or use different files for your Kokkos and NVCC or your CUDA code if you all want to be compiled from the same source. One big issue with Kokkos is that shared libraries are not compatible with device symbol relocation. What this means is that if you want to use shared libraries, all symbols in a kernel must be visible to one compilation unit. So the way you can get around this, if you want to use shared libraries, is that you need to wrap all your kernels into a single file with a bunch of includes, which is what we did. And this actually required a significant amount of refactoring for the different functions in the files to make it all work, especially since we really wanted to share as much code as possible between the CUDA and the Kokkos implementations. What is nice about Kokkos with the CUDA backend is it's completely interoperable with pure CUDA, which means that you can call CUDA functions directly from Kokkos kernels, which makes the incremental porting and migration and validation much, much easier because you can just do things a step at a time. We also had to convert all the data structures to Kokkos views because we really wanted to have full portability between backends. Now, In theory, you don't actually need to do this because you can actually wrap Kokkos views around memory, which is allocated elsewhere, which does make porting of CUDA malloc memory easier. But if you don't want to use CUDA malloc because you're operating on, say, an AMD card or using P threads or OpenMP for the back end, then you actually need to use the views. One thing which we saw was not well supported in Kokkos was the multidimensional arrays, like views of views, jagged arrays really, as opposed to just simple multidimensional arrays. You need a lot of extra boilerplate to make this work with a view of view. So we ended up flattening all these jagged arrays into 1D data structures or padded them out into 2Ds. Kokkos does require explicit host to device memory migration, much like CUDA, and you need to create views on the host to hold the copy information. There are some non-zero overheads to using views, which we saw when doing memory reinitialization and for creating the views on the host to hold it all. While the syntax is somewhat different from CUDA, the concepts are pretty much exactly the same. Use lambdas instead of functions. You have parallel fors and parallel scans and reductions. Maybe not all CUDA features are available on Kokkos yet, but I think in the very near future they pretty much all will be. And you have things like atomics and such, just like you have in CUDA. We were actually able to exercise pretty much every single backend for Kokkos. CUDA, we used a HIP on an AMD GPU. We were able to run the serial backend. We were able to run on the Intel discrete GPUs at Argonne, but unfortunately we can't show those results since they're still proprietary. We're able to use P threads and OpenMP for host parallel studies. And we also did a port of the CUDA to pure HIP to be able to kind of compare the Kokkos implementation of the HIP to pure HIP. And we saw a number of interesting things from this. In general, the CUDA backend of Kokkos had pretty much comparable performance to CUDA. If you look at the simulate kernel and the total event loop. Kokkos definitely puts a penalty on memory reinitialization, and we see this with the reset kernels. And it will also increase the launch penalties. So it almost doubles them in some case if we look at the Kokkos CUDA launch penalty to the pure CUDA one, and the same is with HIP using the AMD GPUs. We notice though that HIP in general, or the AMD GPU in general, has a huge launch penalty, orders of magnitude worse than CUDA, and this is only exacerbated by using Kokkos. So things to draw from this though is that that we see some, basically comparable performance with the CUDA backend to Kokkos, and some overheads from memory initialization and accessing. We also took the CUDA code and we ported it to SYCL. Now this is more of a rewrite as opposed to the Kokkos port, which is really more of an incremental port. There are a lot of different flavors of SYCL available right now. There's the Intel official beta, which runs on Intel CPUs. Well, all CPUs really, Intel iGPUs and FPGAs. They're the closed source code drops for the Argonne A21 developments, which can run on the discrete GPUs. There is the LVM Git version, which can actually have a CUDA backend. But unfortunately, we can't exercise it fully because there is no RNG implementation yet for 1MKL. So this is being worked on. There's the CodePlay version. There's also the HipSYCL, which runs on AMD, NVIDIA, and Intel. There's TriSYCL for running FPGA. As you can see, there are a lot of different versions of SYCL. Now, in theory, SYCL is a single source compiler where you can compile it once and run anywhere with a backend selectable at runtime. In practice, though, depending on where you want to run, you really have to choose a different compiler to target specific hardware. Maybe there will be some convergence in the future, but we aren't there yet. So adding the SYCL data points to the plot I showed earlier, we see some more interesting things here. We added the SYCL running on a CPU and SYCL running on the integrated GPU. So this really isn't a fair comparison to a CUDA port because the integrated GPU on an AMD CPU has many fewer execution units to a CUDA or to an NVIDIA GPU. Also, you're sharing the memory on the CPU, so your memory interactions are obviously going to be much faster. But we can definitely draw some useful things out of this. If we look at the event loop, we see that the integrated CPU is obviously better than just running on integrated GPU is better than running on the CPU. The integrated CPU, the CPU for SYCL looks like it performs better than the Kokkos serial, and slightly better than the original CPU code, or comparable performance to the original CPU code as well. We also see some overheads to resetting the memory on both the CPU and the integrated GPU using SYCL, but this is probably due to the way the memory was being reset, which used about 180,000 kernel launches, so probably not the most effective way of doing it. But we've taken the same SYCL code and on all the different integrated and also discrete GPUs that we have available at Argonne on some of their benchmark platforms for A21, and it runs with basically no modification of the code, which is very nice. So some lessons learned from all of this. The build configuration requirements can be challenging. The whole thing about Kokkos shared libs versus relocatable codes required a lot of code reorganization. DPC++ or SYCL is changing very rapidly, maybe a little bit too rapidly for easy development right now, and things that worked last week may not actually work today. You still need separate binaries for all the different device backends, Kokkos explicitly, and SYCL just because you need different compiler flavors. This has major implications for production code distribution if you want to run on the grid and you don't know where your code is going to end up and which hardware is going to be available on the node where your code actually gets executed. In general, the CUDA to various portability layer concepts translate pretty well. The syntax may look different, but the concepts are pretty much the same. However, there are some overheads to using things like views or buffers or USM memory management. And we see this for both Kokkos and for SYCL. The launch latencies for tiny kernels really kills performance on all platforms. And this isn't really a fault necessarily of the portability layers, it's really a fault of the code that we're using. And unfortunately, I think we see this in many different sort of applications where we really are limited by the amount of work that we can ship out to a GPU, but the portability layer actually makes it somewhat worse. AMD though is at this stage is really bad just because of these huge launch latencies that we see with at least the Vega 56 and 64 platform. Maybe things will improve with RDNA2 and CDNA2 and Instinct. I don't know yet. Haven't had a piece of hardware that we can actually use to test things out. There's still the question as to if we'll be able to get really performance single source CPU and GPU code, meaning that even if you rewrite your code to work well on a GPU, is it going to work still very well on a CPU just because of different ways that you want to target hardware on CPUs and GPUs. And in general, the GPU is very underutilized in FastCaloSim, but obviously if you want to improve things, you can group data between events. On the other hand, this really requires a significant amount of refactoring of frameworks if you want to make this more generally accessible. Then again, you can share a single GPU between multiple processes, so you can save on hardware costs if you want to go that route. Finally, the next steps. We want to look at some other portability layers for the HepCC project. We're going to look at OpenMP or OpenACC, which have very different pragma-based directives. We're going to look at Alpaca, which is a very strong presence at CERN. And then we may also look at Raja, but I'm not sure if we're going to really learn anything that Kokkos didn't already teach us. We're also going to look at other backends. I think what will be very nice is to be able to run SYCL with a CUDA backend on NVIDIA, which will really allow us to do an apples-to-apples comparison to the Kokkos running with the CUDA backend. Work has been started on the QRAN support for 1MKL, which is the piece which is missing for being able to do this right now. We hope to be able to publish some numbers on running on the Intel discrete GPUs, such as the Arctic Sound and the Ponte Vecchio, which are much more comparable to NVIDIA hardware than the DG1, the XELP, which is available right now, using both Kokkos and with SYCL. we can already run on these things on the Argon nodes, but this is very beta hardware, so it really, the numbers that you see there aren't really germane. And we also very much like to run on some of the newer AMD hardware that's going to be used in the next generation of supercomputers, such as Frontier. And we also want to have some better understanding and evaluation of the metrics to be able to say, right, we want to go with Kokkos or we want to go with SYCL. And we really need to do this in coordination with the other test beds that we are evaluating for CCE. And finally, we want to update the FastCaloSim version that we're using to better reflect what Alice is using right now, using things like more realistic particle scenarios and to be able to integrate into the Atlas repositories. And that's it. Are there any questions?
Thanks, Charles. So went a little bit long, but yeah, Attila, go ahead.
I think it was on slide 10 where you showed the performance results with SYCL. Just in the final column in the event loop times, I imagine that the original CPU time, that's running on a single thread, right?
That's right.
Okay. Yeah, this is well in line with what I've been seeing in other places as well. Okay. And yeah, maybe just as a joke, since there aren't any other hands up, with RDNA2, we might want to invest or we might want to buy a couple of PlayStations or Xboxes right now, because that might be the best way of actually getting our hands on one of those. But, yeah.
Yeah, they're definitely hard to find right now.
I see a question from John.
I'm not sure if it's a question again. I am rather surprised that you had to make so many changes by using the code into includes. Basically, it sounded like you had everything into one compilation unit, everything that was going to be done because of this. Is that correct or not?
That is correct. Now, some of it has to do with the structure of FastCaloSim. FastCaloSim is relatively small. It doesn't have a lot of, the kernels are pretty small. So you only, in theory, have to you have to put everything into one compilation unit for that, one specific task. You can have multiple kernels which don't actually need code or symbols from other kernels, and you can have those in separate compilation units. But you can have your something which is running for muons on the GPU, which doesn't care about what's happening inside of the the inner detector. And so as long as those two kernels are completely separate and don't need any symbols from the other ones, then you can have them in separate compilation units and separate files. But the way things work with Kokkos right now, if you want to use shared libraries, you have to put everything inside of one file. You basically have to resolve all the symbols inside of one compilation unit. So you end up putting everything inside of one file.
I believe there is a bit of a misunderstanding here, and you may not have seen it just yet, Charles, but I wanted to follow up with you about this. But in the end, I understand why Kokkos decided that if you compile Kokkos itself, the core Kokkos library, into a shared library, then they would require you to put all of your device code into single compilation units. But it should still be possible to compile the Kokkos code into a static library and then include that static library even into your own shared libraries if you want to. So as long as you can put all of that code, the Kokkos code and your code, into the same module, into the same shared library or the same executable, it should work. Then you should be able to separate device code into multiple compilation units.
Yes, you can do it that way. It complicates the build situation, considerably. You really have to do a lot more hacking of your CMake files. And one of the things we were really trying to do was to use as much of the original build infrastructure as possible. So, because we really don't want to have to, with something like FastCaloSim, which is relatively small, we could do all of this. But then if we wanted to take this and work it back into, the full Athena build infrastructure or CMS or whatever, then it becomes much more complicated.
Okay, I see one. I think you can take one last comment, a quick one from Matti.
Yeah, I'd like to just follow up on what Attila commented about this building Kokkos static library. That indeed works. I mean, you can build Kokkos as a static library and link that against several shared libraries which use different kernels, and that works fine. But you still have to, as Charles mentioned, you still have to put everything of a single, all device symbols that a single kernel uses, they have to be in one translation unit.
I'm a little bit surprised by that.
Because of limitations of NVCC and how it handles device linking.
No, but are you sure that you meant compilation unit and not in a single module? Because of course you can.
I specifically a single translation unit.
Okay.
Because in order to link two object files with device code, you basically need the same features. I mean, the separate linking or separate compilation feature, which requires relocatable device symbols, which you cannot use with Kokkos. They explicitly disallow the use of those, essentially. Or something
I think
like
this might be something we follow up offline, but thanks for the clarification. So just yeah, thanks again to everyone who presented in the second half of the session and for the robust discussion.